All right, thank you very much for coming to our weekly seminar in the department. Today I'm very excited to have Mike Short from MIT here. Mike graduated with his PhD from MIT in 2010, shortly after I graduated. And he and I were actually working on the same topic, so we knew each other from back at the time because he was working on lead bismuth corrosion of iron silicon alloys, and I was working on lead bismuth corrosion of other alloys. And so we knew each other from back then. And then he was appointed as an assistant professor in 2013, and worked on numerous topics, one of which he selected today to talk about accelerating innovation in nuclear material science. However, he also, several of our undergrad students graduated from here working in his group, and some of you remember Rachel Koenig, who was part of the Blacksmithing team and is now taking that
She didn't tell me that.
She didn't tell you that?
No, that's awesome. We have
There's a beautiful movie of her hitting metal and all that.
Oh my God.
So yeah, she was part of it.
Okay, now I have to show something else. Keep going.
Okay. And so several of our graduates work in Mike's group. And particularly noteworthy is his work on Crud formation in reactors, fouling deposits in energy systems, and quantification of radiation damage per stored energy fingerprints, which also was selected as a recent NSF Premier Award. So with that, Mike, I want please go ahead and talk to us about accelerated innovation in nuclear material science.
Sure. Well, I think who all here is on the blacksmithing team or was involved somehow in the sword? Okay, there's enough of you guys then. So I think I'm obligated to show this now, because if you can do that, you can definitely do this. So something else I do, I took from the blacksmithing days, is you can take it in for use silver and gold, in this case white gold. So I just made a set of wedding rings for my brother. And this is way easier than working with steel. But for any of you that are thinking of transferring your knowledge from steel to other metals, it's a little different. Annealing is really different in that you actually have to quench right away. Rolling is super easy. But you know, with the steel, if you heat it up and you quench it, you make it brittle. With precious metals, if you heat it up and you let it sit for a while, it becomes brittle because the grains grow. So you have to quench it very quickly in order to stop it from brittling, or your wedding rings crack and your wife freaks out. Yeah. I finished mine the morning of the wedding, after screwing up twice. Classic, you know. What? Yeah, I started 3 months early and I screwed up enough times that in the end I was like, all right, I just learned enough lessons to. I had an onion ring as a backup. You know, who knows? But if anyone is interested in this link, I'll send it out. I just finished the video.
Oh yes. Okay.
Yes. Okay. Because I also just learned that you're also leading the blacksmithing. I didn't know that, Professor Ferrier.
That's there you go.
Wow. Yeah. So love the connections that got between here and Berkeley. So I see a bunch of my former students, and I've got a bunch of your former students, and I'm going to talk a little bit about what some of them have been working on. I'm going to hijack my talk and actually talk about 3 things at a little less depth, mostly so you don't get bored, and you can see kind of the variation in things that we do to try and speed up innovation in nuclear material science. Now, I'm going to put something out there that most people don't like to hear, is that we suffer from a lack of innovation. It's why the field is dying. It's why light water reactors, I'll show you what's happening to them. And a lot of folks will challenge me and say, well, can you quantify that statement? What makes us less innovative? I don't necessarily want to do it, but there's other people who do, and come up with empirical indices of innovation in a field. Now, yeah, you can tell from the number of decimal points that this is not rigorously derived from any analytical anything. But when you look at things like how many publications per capita in a field per year, and especially the number of times they cite each other within the first 3 years, the amount of language and patents that's common between each other. These folks at MIT looked at what we said are the 30 fields that are going to shape our future, and nuclear came in dead last. Way behind machining equipment and food science and other stuff that just like isn't that interesting to most people. Don't let the negative value worry you, because again, it's empirical. But it does show qualitatively that we are slow to innovate, and a lot of that is due to the inherent difficulties in doing anything in our field, right? You guys are blessed with the giant basement lab of horrors, which is, you can do anything you want down there, you can make things radioactive, that's awesome. It took a lot more fighting to get that established in my lab at MIT, and everyone's so scared of what we do that we had to either build or buy duplicates of all the equipment on campus just to get it work done. You have a question?
Does that also take into account the relative number of people in each field?
So this should be publications per year per capita. So it's normalized to that. But then the number of citations is just the number of times papers are cross-cited within the first 3 years. Now, I didn't make the index, so I would improve upon it, mostly to make us not look so bad. But the picture is pretty bleak because this is how much nuclear capacity we're going to have by the year 2050, which is none of it. And this assumes that all of the reactors get their 60-year licenses and then don't apply for any more. And so when I came into this field on my own, really about 5.5 years ago, I figured there's a lot of data that needs to be taken to break some catch-22 scenarios. We need radiation testing data to build the reactor, but you have to build the reactor to get the radiation testing data, is the classic catch-22 in this field. So I decided that we're going to set out to build monstrous experiments that nobody else wants to bother with to break some of these catch-22s. One of the current problems affecting light water reactors is the buildup of crud. It's what you think it is. It's junky stuff that builds up on the fuel, corrosion products from elsewhere in the reactor. And it turns out using an all-optical design principle, we've developed coatings that you can't get crud to stick to them. And that's in all of our lab-tested conditions, but we're slated to do some lead test rods in a commercial reactor next year. So we will find out whether this works in the real world or not. And that's one of the other things we try to do is go from lab to reality in 5 years. It's so far we've done it in maybe 6 or 7. That's close enough order of magnitude. No, it doesn't really cut it for us. We'll all be gone in an order of magnitude more time. So we don't really have that much more time to wait. We're also looking, and this is, I know there's a lot of people here working on molten salts, at the conditions where radiation can decelerate corrosion. This is a controversial hypothesis of ours. We've only got one paper out that gives a hint of the results, but I'm going to show you a lot more of the details that aren't published yet and see if you've got any questions on that. And then finally, a much, much, much faster way of getting radiation damage information using an all-optical, non-destructive evaluation technique called transient grating spectroscopy, where we can do end-of-life materials experiments like determining the onset of void swelling with 1,000 times the dose resolution in 5,000 times less time. We take experiments which used to take a year and we do them in an afternoon. And I'll show you how we do that in a bit. And I'll start out with a project I call Designing the Ultimate Crud-Resistant Material, or Making Nuclear Teflon. That's really what we're trying to do. We're trying to make materials like Teflon that nothing stick to, but that don't melt at reactor conditions. Because the melting point of Teflon is the operating point of a pressurized water reactor. So, not going to work. And when Teflon melts, it makes hydrochloric acid gas. And other problems. For those who haven't seen CRUD before, it's a fake backronym for Chalk River Unidentified Deposits. I introduced it as an acronym for Chalk River, whatever, and the folks from Chalk River stood up and said, "How dare you besmirch our great laboratory with this horrible acronym." It's corrosion products that come from elsewhere in the reactor, like the piping, the steam generator, and played out here on the fuel as this brown crusty stuff. It's like 20 to 100 micron porous media that costs the industry between $150 and $500 million per year. And in this day and age, when natural gas is cheap and other renewables are over-subsidized, you can't compete like that. So the actual cost is it comes out to something like $1 million per fuel cycle per reactor from ultrasonic fuel cleaning. Because that's how much extra outage time it takes to clean off the crud from the fuel. And then you actually have to buy more fresh fuel to reduce the amount of oiling that's causing the crud to form. And then if things go wronger, you lose about 10K per percent power per day from required derating of your plant. And if crud causes any sort of severe corrosion issues like leaking fuel, you've got to shut down early. And that costs you $1 to $2 million per day in lost power. And there's worker dose concerns, like this crud gets radioactive, it gets spread out around the plant, and it then takes 32 or 40 welders to do the job of one, because you have to keep swapping people out when they hit their maximum radiation dose. And so for decades, the industry has been empirically trying things like ultrasonic cleaning or electropolishing of the fuel ultrasonic cleaning, changing fuel loading patterns, tweaking water chemistry, and things have kind of worked, but then when power uprates came back, the crud came back with a vengeance. It's still an issue that people worry about. And so we thought, what actually makes crud stick to fuel cladding? And we looked at all the possible surface forces, and we figured it came down to induced dipole interactions, or van der Waals forces. There's no magnetism going on here. Zircaloy is not magnetic. There's no hydrogen bonding. There's no biofouling, because nothing survives in the primary loop. And due to some measurements that we've made a little earlier, we know that the static dipole component of surface forces kind of drops off at around 200 Celsius. That leaves van der Waals forces. So we would take particles of crud, which we grew in one of our loops that we'll show you in a bit, and focus right in on the interface to say, what makes this particle stick to that cladding? That's what we really want to know, because if we understand the sticking mechanism, we can design materials against it. So there's a simple equation relating the van der Waals force between a sphere and a piece of cladding, which we'll call the sphere the crud, and its radius and the distance between the sphere and the cladding. Anyone know why the distance never goes to 0 and the force never goes to infinity? Why can't anything ever touch anything else? That's a pretty general question.
Repulsive forces?
There are repulsive forces, but you can't get anything more than an atomic distance apart, right? You can't have atoms on top of each other. You can't have, yeah. So you have always an atomic distance, so there's a finite amount of van der Waals force, so this does not diverge to 0, to infinity. A lot of people always ask that. And we can look at the equation that relates that force constant, the one thing I didn't introduce, called the Hamaker Constant. And this relates the optical indices of refraction between the clad, the fluid, and the crud. And it's a little complicated. This is actually a simplification. So what I would advise you is, don't look at the front, because that's just things you multiply by, constants. Don't look at the denominator, because the denominator is just kind of a big constant. And all you're left with is a couple of differences in the numerator. We can't control what the crud is in the nuclear reactor. It's going to be a function of what the reactor is made of. But we can control the coatings on the cladding. So if we coat the cladding with something that has the same optical properties as the fluid surrounding it, then that should stop crud from growing, because it will shut down the surface forces that cause things to stick in the first place. So the way that we test out and measure these coatings is with atomic force microscope force spectroscopy, where we take a little cantilever, a little bar of silicon or silicon nitride, affix a little bit of heat-resistant glue to it, so you can see the bar right there, and then pick up a microsphere of silica. It has to be very spherical and of a very well-known radius to calculate the surface forces. Grab it with a nanomanipulator, pop it on, heat cure it, and measure the stickiness of different materials to zircaloy fuel cladding or to the coatings that we apply to it, and compare it with the base surfaces that you'd find in the reactor like magnetite. And luckily our experimental predictions, or theoretical predictions in red, and the experimental predictions in blue match up pretty well, especially for the really slick materials. We're able to make things that are routinely 20 to 50 times less sticky than zircaloy cladding. You'll notice there's always a little bit of a mismatch between the experiments and the simulations. That's because there are other surface forces at play, but van der Waals forces appear to be the dominant one, as is the mostly good agreement between experiment and calculation. But it's not just enough to do this in a room temperature AFM. So we built the first monstrosity of our lab, the Crud Loop, which is a reactor without the radiation. So it's just a big flowing loop that goes to the same pressure, temperature, heat flux, flow rate, water chemistry as you get in a reactor, but no radiation. And we slide rings of zircaloy onto our heating rod and coat half of them in our potential crud-resistant material. So this way we have a built-in control. The top half has our slick coating, and the bottom half is bare zircaloy. So if there's any mismatch between thermal fit or slight dimensional tolerance between these rings and the heater, we account for that. We then take those rings off the experiment, which get pretty cruddy, take SEM images and look at how much of the surface is covered in crud. And then we plot that as a function of material and as a function of some various other image processing parameters. And we end up with a graph like this. And the way to read this is up is good and down is bad, and the x-axis is just different materials. So the materials that show a positive crud reduction actually reduce the amount of crud deposition repeatedly at PWR conditions. And these are 2 sigma error bars. So we know that these resist crud, at least these two resist crud pretty well. And they've got to be stable in high temperature, high pressure water. So these should be pretty good in terms of moving to the next stage for a lead test rod. We've also had these coatings in the MIT reactor for half a year in a flowing PWR loop. We're currently analyzing these coatings to see if they survive radiolysis. So that's another binary yes or no question. But we can go a little further with this optical design principle, because industry may be happy, but the scientist in me says, how low can you go? So we started looking at some fluorine-based coatings, which have very similar optical properties to that of water. If you just look here at the visible index of refraction, that between water, cryolite, calcium fluoride, and even crystalline silica are really close. So we tried using those coatings and compared to some silicon substrates, glass substrates, an Indian tin oxide heater that we happen to have lying around. These ones were off the chart. In fact, they were so slick that some of the error bars crossed the x-axis. But one important thing to note here is that no matter what foulet we threw at these slick coatings, all the stickiness was statistically the same. So these are what's called foulant agnostic. And the theory predicts this as well, but now we've been able to experimentally verify it. And then last thing for the simulationists in the audience, we've also done DFT, or atomistic density functional theory calculations of the slickness of these surfaces, and everything agrees pretty well. So that the theory and the lab scale experiments and the reactor scale experiments all seem to be matching. And that appears to be enough information for a plant site manager to say, yeah, okay, put this in my reactor, I'll accept the risk. Anyone know what the risk is? What are they signing on for when they're like, we'll put your material in our commercial reactor for which we have a contract to deliver power, right? An outage, let's say we end up causing a month outage, that's a $50 million mistake, if all goes well. Because you have to find the leaky fuel element, remove it, replace it with a new one, do all of your inspection and testing, and then shutting down and starting a reactor is not just kind of a switch, it's like often takes a week. So you're on the hook for a lot of lost money. Yeah?
How do you characterize the film on the material? I mean, is the film sticks really well to the cladding?
The film adheres really well as long as it's thin enough. So if you grow...
How do you know?
We can try scratch tests and fretting tests. So we're actually buying a fretting machine to make sure that, let's say you have to slide the coating into the spacer grid, right? That spacer grid, when it sits there gripping the cladding, it's going to be vibrating about. And you need to make sure that you don't cause early fretting, let's say. But let's say, I'll play devil's advocate here, and let's say the coating doesn't adhere so well, and 20% of it ends up flaking off. That's okay. If you can remove 80% of the crud on a volumetric average, you still win in terms of preventing the outages and the power derailings. So this doesn't have to work in the perfect sense. It just has to work well enough. Does that answer your question and maybe another one? Yeah. And a little preview of what's to come. There's one experimental gap that I haven't mentioned, and that's what is the actual adhesion force at reactor temperatures? No one's ever measured it because no one's ever been able to. So we've also constructed monstrosity number 2, which I want to jump into, is high pressure, high temperature atomic force microscope. So we built an AFM that goes to 150 atmospheres, 350 Celsius, and in liquid cell. And so we're actually able now to characterize how sticky things are in reactor conditions. The only difference here is we have no radiation. I can't say much more because we're disclosing this for IP reasons, but I probably shouldn't show you that. But I wanted to in case anyone had any ways they wanted to work together. So I'll pause here for a minute and take any questions you have on the Crud project before moving a little further into Crazy Town.
What about thermal conductivity of these coatings?
Doesn't matter. They're so thin that they're not as good as metals, right? These are ceramics. They're often not too good. But we only apply 1 to 200 nanometers. So like I mentioned before, the coating has to be thin, so you stay in that epitaxial limit, and we can't get these things to flake off. But if you grow them to be a micron or so, then 1, they become like a thermal barrier coating, and 2, they crack and flake off. So there's a sweet spot of a few hundred nanometers where it doesn't matter for neutronics, it doesn't matter for water chemistry, it doesn't matter for adhesion.
It still doesn't matter. If you're peeling off, then you're creating hot spots.
Not quite. So with a 100 nanometer coating, the thermal conductivity of the coating may be low, but the total thermal resistance of anything that's 100 nanometers thick is not very high. So you may have slightly hotter spots, I'll give you that, but not of much consequence. And we expect there to be places where the coating scratched off when we load it into the fuel spacer. So what? We'll have scratches. We can deal with that. Yeah.
Have you looked at the corrosion resistance of the coating itself? Because you could expect to lose 100 nanometers just through oxidation.
Normally, yes.
Okay.
That's what the MIT reactor tests were for. Was to put it in a flowing PWR loop with radiolysis and just answer the binary question, is the coating still there? Answer the other binary question, did it destroy your zircon? That's what we're working on now.
How are you doing the depositions?
With PVD, physical vapor deposition. It's good. Yeah.
But the PVD immediately raises the question, it's not scalable, right? So you cannot make 60,000 fuel rods PVD coated in a reasonable amount of time.
You actually need 1 million, or about 800,000 to coat the world's, the US supply every year.
Very
And actually, yes, you can. This is one of the big side things that we've been working on. Been working with 2 companies that coat flat panel displays, one in the US, one in Japan. They have a PVD chamber which you can drive into, because they coat 4 meter square displays. And so we've been working with their engineers to design an insert to that existing machine that you can take a carousel of a couple dozen rods and rotate them, and you can apply this coating to a full 4 meter rod in 10 minutes. If you add the pump down and venting and reloading time, it's an hour per batch. And so at 24 rods per hour, running 24/7, 365 days a year, you need 1 machine to coat the US supply of rods every year. Now, note the fact that you don't have to coat every rod. You only have to coat the 10 or 20% hottest rods. And you don't have to coat the whole rod. You just have to coat the hot spans, maybe the 2 meters with the most boiling. And then all of a sudden, you've got capacity to spare. So this project is funded by Exelon, and they simply said, okay, research is cool, but if the net positive value is negative, we will not fund your project. You have to show us ahead of time that you can do this at scale. And so that was a requirement to get this funding. Then we found out that we were a little over-optimistic, but we've got it down to about $25 to $30 extra per rod, and our goal is to get to 10. Once you get to 10, they're like, we'll do this for the fleet, which is kind of exciting. Yeah, this is one of our biggest worries. It's like, great science, but what about scale? Any other questions on Crud? Cool. So now I want to move into something that, I don't know if anyone here is from or is interned at Kairos, but this might be of particular interest to you guys, especially if it ends up being correct, and I'm not gonna posit that it is, but we have strong evidence in favor of it, is that we're seeing radiation decelerated corrosion in certain conditions in molten salts. And I'll flash up a picture that probably everyone has seen before. If you've seen molten salts, is they attack structural materials, often by intergranular corrosion, especially at the lower temperatures, kind of 650 C and below. Intergranular attack is bad news. So this is what 316 looks like. This is also what Incaloy 800 looks like, just on a smaller scale. The big question is, when you add radiation, what's going to happen? When we got this project funded from Transatomic, which doesn't exist anymore, we promised them that we would get to the acceleration factor, assuming that radiation would accelerate corrosion in molten salts. There's only a couple people in the world that have tried this before. Peter's one of them, I found out. And there's another group in Russia that's done this with electrons, and that's all we could find. Couldn't find much published, but explain that a little bit, right? Yeah. So we built our own beamline, which is going to look suspiciously like the one that Professor Hostman built at Los Alamos. It allows you to have a vessel of molten salt with a thin foil sample and a proton beam blasting through it at the same time. So the protons go through the metal into the salt, so you just induce radiation damage and some funky salt chemistry effects. And you get a built-in control sample, because by masking off your beam, you get a corrosion and a radiated region in the center, and a corrosion-only region on the outside. So you have an apples-to-apples comparison in the same test, with nothing else varying except the amount of radiation hitting. And just to show you another cross-section of what I'll explain later, there'll be a region in green that only sees salt corrosion. There'll be a region in yellow that only sees corrosion and irradiation. The salt we use is Flynac plus europium fluoride, and that's to pull the corrosion potential down to simulate salt fuel, which is a lot more corrosive than clean Flynac or clean Fly. So we went for a worst case scenario, like if somebody wants to build a molten salt fueled reactor, what's it going to be like? And so here's what happened. If you look at the unirradiated side, you can see a mess. where after 4 hours, the salt has penetrated through the 25 microns of foil, and you can actually see molten salt creeping and oozing between the grains as one would expect to see. When you move over in the SEM and look at the irradiated side, it comes out clean. Except for the occasional impurity and one grain that we found where the salt did penetrate through. So the effect is actually so strong that you can see it with a naked eye. In fact, this picture was taken with a cell phone. The shiny side in the middle is the beam-facing side of the foil, and the lack of white sparkly stuff, that's just metal you're seeing. Where the white sparkles are molten salt that has oozed through the foil and eventually caused the sample to fail. And in the SEM, you can actually see the curvature of the proton beam line in cleanliness, not in filth, which is what we would have expected to see. And so quantifying this a little more, we tried repeating this over and over again, because at first we didn't believe our results. I'm sure, I don't know if you guys have heard this expression, an experimentalist is the only one who does not believe their own results, and a simulationist is the only one who does. Not to insult the simulationists in the room, we do both, and we're equally skeptical of everything that comes out of our lab. So we repeated this test something like 15 times to make sure that we really could control what's going on. And I'll show you a few images from different proton beam currents, all at 4 hours at 650 Celsius in the same fly neck and europium fluoride. When you look on the surface, the irradiated region is clean. If you look at a cross-section, to get a little more quantitative, you can actually see very orientation-dependent corrosion that only penetrated about halfway through on the irradiated region and made it all the way through in the unirradiated region. So we think there's about a factor of 2 slowdown at these conditions, which is awesome, right? It's not an acceleration. Lowering the proton beam current a little bit, same picture on the front, and in the cross-section, you see that the salt didn't quite penetrate as far in the radiation side, but also got all the way through on the unirradiated side. Cut the proton beam current in 2 again. Everything looks clean on the front, but the cross-section reveals about double the penetration in the unirradiated side once again. And so there's 2 competing effects going on here. There is an effect of the proton beam changing salt chemistry that I want to highlight first. So here you're looking at the unirradiated part of the sample, and left to right is increasing proton beam current. And you can see that the salt gets more and more corrosive the more protons we pump into it. But when you move to the irradiated side, you see this universal decrease in the amount of corrosion. So radiation damage appears to make the material more resistant, but proton irradiation makes the salt more corrosive. One of these effects will not be present in molten salt reactors, because we're going to use neutrons instead of protons. And we won't be changing the salt chemistry nearly as much. There'll be a little bit of activation, but tritium production, but not every neutron is going to become a hydrogen atom like we have with the protons. And so we think this is a pretty robust deceleration of corrosion in molten salt. And the mechanism we're proposing is classic radiation-induced segregation. So this is a TEM line scan showing chromium depletion and nickel enrichment on a stainless steel grain boundary. This is what makes your stainless not stainless in light water reactors. And this is bad. But in a fluoride-cooled salt reactor, there's no protective oxide, there's no passivation, there's no such thing as stainless. And so pulling the chromium away from the free surface by creating point defects from radiation would preferentially pull the chromium away from the free surface and pushes the nickel towards the free surface, depletes chrome from where the salt can see it, and causes this decelerated corrosion. So to show it a little more graphically, here is a corroded grain boundary from one of our samples, and normally chromium will move into the grain boundary, come out this superhighway, and get dissolved into the salt. And there's a defect gradient near sinks only present with radiation, which causes a movement of chromium in the opposite way, and decreases the net loss rate of chromium, and therefore slows the corrosion rate in molten salts. There are regions where this shouldn't work. If the temperature gets too high, you switch to a bulk or an intragranular corrosion mechanism, and this shouldn't work anymore. You also won't be able to support that much of a chromium depletion. So once you pass 700 C or so, which we've done in the lab, this effect shuts off, and you get an acceleration of corrosion with irradiation. But this should also work in liquid metals, because in liquid metals, in the reducing condition, the corrosion mechanism is often chromium depletion. And so I hypothesize, and I and hopefully Professor Hoseman will be trying this out separately, right? To confirm each other's results. Whether this is true. We built parallel facilities. So, you know, I don't think he knew that I was building this, and I didn't know that they were recommissioning ICE 2 at Lano. Found that out when the papers were going out, and it's like, great, so we can verify stuff, right? That's what you want in science. Not, you know, who scooped who, but we agree with each other. Or if we don't, then there's some explaining to do. So, do you guys have any questions on this? For me to do a little more explaining. Yeah?
Can you exclude this a temperature effect? When you the current, right, you are also increasing the temperature by, what was this? Almost a factor of 2, right? Because so you're pumping more current in means the sample heats up more.
Mm-hmm.
I don't know where a thermocouple sit, but one challenge is always that can you verify, do you know what's your temperature at the backside of your sample on the salt contact?
We went through ridiculous pains to do that, actually. So we've built a full COMSOL model of this entire beam length. And while we can't put a thermocouple on the back of the sample, we spot welded one to the front, as well as 17 other locations. Really, like we just went all out because this was one of the big questions, is beam heating doing something? I would argue that beam heating would accelerate corrosion because you would reduce the amount of radiation-induced segregation. But what we found is that based on all our COMSOL fitting, the beam heats our sample by about 10 to 20 Celsius, depending on the beam current. And so as we go, you know, we go down a factor of 2 in the beam current, we're down at about 10 Celsius. Not a big acceleration. Should be about a 2 times acceleration in any Arrhenius-based corrosion rate. That's not going to be present in reactors either. So what I showed you in this data here has 2 effects that are making the story look a little bit worse for us, but it's actually going to get better. One of them is the chemical effect of injecting protons into the salt, changing the potential. And the other one is you're not going to have localized beam heating in a reactor. Everything's going to be equal.
So what's the level of dPA or fluence this would be equivalent in terms of difference?
Good question. So this is 100 to 500 times the dPA rate that you'd see in a reactor. So we push the protons in, we're getting maybe 0.1
When
dPA.
you say that you see in a reactor, where in a reactor?
So I'm thinking middle of the core, let's say.
Middle of the core.
Outside the core, it's going to be even worse. So, you know, when you get less neutrons, I expect you're going to get less of a slowdown effect. The big question now is, if we reduce the proton beam current by a factor of 100, will we still see a slowdown? And if we see an acceleration, would there be a slowdown in the neutron case? But again, now I want to bring it back to say, what's good enough, right? Let's say in the end, radiation doesn't decelerate corrosion, but it also doesn't accelerate. Then your worst case scenario will still be unirradiated test. So I would think that means you can cut down the number of fully irradiated tests you need to do to convince a regulator, yeah, this isn't going to be an issue. So even if there's no acceleration and no deceleration, that's a success for the molten salt community. Yes, you? Yeah?
Has there been any control runs of just basically putting a plate, you know, ion beam on for 4 hours and 650? And on a similar line, I don't know how you do it with the setup, but having an isolated circle just in the very middle, and having a control run with no beam, and then an isolated circle control run with the beam.
So the answer to your first question is yes. We do about 1 control run for every real experiment. And so we do lots of no-beam corrosion experiments. For example, we tried changing the europium tri- and difluoride potential to just get the effect of europium potential on corrosion. And we just use this beam line as a little molten salt chamber for that. The other controls that we do that I didn't mention, in order to test whether this hypothesis is true, the effect should switch when you go to a non-alloy, like a pure metal. Because then the salt should get more corrosive and the spot in the center should actually get worse. So since it's coming up, I would like to show you the results of that experiment. Since I take it there's a pretty big molten salt community here. So this is what we ended up getting. This is a pure iron foil. And what you're seeing here, that scale bar is not an error. This is a composite of like many thousands of images in the SEM. We wanted to get an SEM image of the entire foil. And this was pure iron. So by our hypothesis, if protons decreased salt corrosion, then we should actually end up getting the same sort of thing. Or if radiation actually decelerated corrosion, then the regions should switch. The sort of jaggedness of the bars here represents the corrosion depth. And so what we saw is we had a big corrosion spot in the center. When you look at spots in the center where the radiation was and on the outside where the radiation wasn't, you see that the center got intergranularly corroded to hell while the non-irradiated part looks kind of like a textbook picture of iron. And so the region switched position, which is awesome. We also trained a machine learning algorithm to identify where intergranular corrosion was worst, and we're able to image the corrosion spot and verify that it was indeed the same dimensions as the beam, which is pretty cool. And the fact that it's fuzzy is actually expected too, because if this is a chemical effect of the protons making the salt more corrosive, then it shouldn't be localized to a perfect circle. Chemicals spread and there's convection currents in the cell, and it should be messy. Not like we saw with the radiation decelerated corrosion. And so we're able to confirm our hypothesis and disprove the competing ones, which were brought up by a lot of folks that know this stuff. And finally, your question, yeah.
Have you tried with that and other proton energies? You
No.
have 3 MeV.
Sorry?
You have 3 MeV.
Correct, yeah. So we didn't try other proton energies because we need the protons to get through the salt. Which would be equivalent, though, to using a slightly thicker foil. Because what matters then to me is what is the damage level or the proton beam energy at the edge of the foil that's facing the salt. So we can make slightly thicker foils. But our goal is always to make sure that the protons pass way through the foil and end up in the salt. There's also activation concerns, which at 3 MeV, they're just starting to pick up. And if we went to 4 or 5, things would get very toasty. We'd make a lot of neutrons. Right now, we have to let things cool down for about 4 days. And that's acceptable. Any more than that, and things would get slow again.
But
Yeah.
did you actually test, look for grain boundary segregation or not?
That's in progress up the hill. Yeah, so we don't have the capability or the skill to do that. So we sent some of these foils to Yang Yang, who just joined LBL, and he's going to be checking exactly for that. I don't know if you guys have met Yang Yang, but I recommend you do. He's a pretty bright guy. Cool. Any other salt questions? We're moving on to something even completely different here. Cool. So then the last part I want to talk about is really accelerating innovation in nuclear materials science. This is the 1,000 times more resolution at a 5,000 times less time project. And the problem that I want to get at is void swelling, where if you blast materials with enough neutrons, or really any other type of radiation, they form pockets of vacuum that cause them to physically increase in size, much like you would expect to see in a movie if this were a rat or a human drinking radioactive waste. But in reality, this happens with metals. And it can really ruin your day. Like in this picture of fuel channel boxes from a Russian sodium-cooled reactor that failed because of void swelling and reduced cross-sectional area. Because once you get to about 10% void swelling, you get 0% ductility. Everything's brittle and everything falls apart. So we can do these tests in the MIT reactor, where we can get about 1 dPa per year, but if we want to know whether this reactor is going to last for 50 years, we have to irradiate for 50 years. If you have the right connections, you could get into the Bor 60 reactor in Russia. I am working on those connections right now. It gets harder by the day as Trump and Putin fight and fall back in love. You know, no matter what happens in their relationship, things get worse for us. So instead we use ion accelerators. I'll be particularly excited when the 7 MV accelerator comes online down in the basement that I just saw, because that's about the energy we need to do this stuff. So we can irradiate at like 5 dPa per hour, but then the problem becomes the analysis. So who here does any sort of TEM analysis in irradiated things? A little bit. Would you describe that as a slow or a quick process? Quite. So let's quantify what you might be in for. So this graph was made by a former student at the University of Michigan, and it shows the void swelling resistance of 3 advanced alloys. I'm not going to get into why they worked or didn't, but I wanted to calculate how much time it took to make this graph. So there's 21 data points on this graph. Each one is error bars, so we'll assume it was 3 samples each. Every sample had to be prepared and irradiated and analyzed. And I asked Dr. Ghetto how long did each of these steps take, and she gave this amount of time. Repeat for 63 samples, and it took over a year to generate this graph, right? How many years do you typically spend in grad school here?
Not enough.
9? 9 graphs could be a pretty solid PhD, but 3 or 4 is not quite cutting it. So this is not fast enough. And I really wanted to get at void swelling because this is one of the things that does destroy reactors in Russia, because Russia has fast reactors. And I would really like for us to have fast reactors, but this is the catch-22, is we don't believe the quality of a lot of things coming out of Russia for, I think, mostly political reasons. There are some issues with data fidelity sometimes, but honestly it's a cultural thing. So just kind of homebrew a faster capability. We looked at all the different techniques that could maybe measure void swelling maybe, and settled upon transient grading spectroscopy, which is a picosecond pump probe, all optical, ultrasonic, non-destructive, other adjective technique. I'll show you how it works. We take 2 lasers and interfere them on the surface of the material that we want to irradiate. And anywhere where the lasers constructively interfere, you get a little localized region of heating. This projects lines onto the sample, so we're taking a cross-sectional cut of this. And these heating lines launch surface acoustic waves which diffract other probe beams. And we measure the change in diffraction contrast on a fast avalanche photodiode. And we get a signal that looks something like this, which encodes a number of material properties. Like the red line here, if you fit to an analytical model, it gives you thermal diffusivity. The green line tells you the wave persistence, or the rate of energy dissipation of surface acoustic waves, which are supposed to be lossless, unless there's junk or precipitates in the way. And a Fourier transform of the blue signal gives you surface acoustic wave speeds. So you can watch the speed of sound, the Young's modulus, the Poisson's ratio, and elastic anisotropy change with radiation. Now these might not be the parameters that you want to measure directly, but if they correlate with void swelling or other stuff, then you can use them as fast indicators of what's going on. And you can tune this probe to measure different depths in the material, and this is where it's really well suited to ion irradiation. Depending on the energy of your ion beam, you might be able to penetrate somewhere between 1 to 10 microns into a material. So you want to interrogate that 1 to 10 microns, right? So by changing the angle of attack of these lasers, you project a different transient grading spacing and elastically probe different 1 to 10 microns of the subsurface material. So a lot of people ask, is this a surface technique? And that depends on who you're talking to. If you're talking to a radiation person, the answer is no, it's a bulk technique. Because what's happening 10 microns down is the same as what's happening 100 microns down. But if you go to 1 micron or less, then you've got surface effects to do. So I want to show you what we've done with this as an example of what this technique can do, show you where we're moving into, and then have a cry for collaboration to see if anyone else is interested in knowing how irradiation affects materials quickly, how you can work with us, because we're just standing up a new user facility. We first looked at things like perfect single crystal niobium and looked at their thermal diffusivity change as a function of radiation dose. Now these irradiations took like seconds because of, the silicon ion irradiation. It does not take long to get to 0.001 dPa. We actually had to design a circuit to quickly raster the beam because we couldn't blank it fast enough to get this low of a dose. And we see that at a very low dose, the thermal diffusivity plummets by a factor of 4. And this is due to lots of point defect creation, and those point defects aren't very mobile in a high melting point material like niobium. With further irradiation at room temperature, the thermal diffusivity recovers to about half its original value, because TEM experiments show that these defects cluster together, and if you have more point defects in fewer big blobs, they don't scatter the electrons responsible for thermal transport as much, and the thermal diffusivity gets better. So if you want to know really well, what is the thermal conductivity of your reactor materials and how is it changing? If you could do this in situ during irradiation, then you could get this data at ridiculous resolution. So guess where we're going with this, right? We did a classical void swelling study of single crystal copper with copper irradiation. Made basically the same kind of graph as Dr. Ghetto did for one material, but this took us half a year. We were able to show with our TGS technique and TEM backup that when the surface acoustic wave speed started to drop, that's when the void started to show up. So we have an indicator for the onset of void swelling, but it still took forever, right? This graph took 6 months to make. So we conceived of and built an in situ ion beam transient grading accelerator system at Sandia National Lab, which is a user facility. It's in Khalid Hattar's ion beam lab, and if you want to come use it, you don't have to pay for it, you just have to write a proposal. And I don't think I get to review them either. It's unfortunate that I have to either write proposals or pay $7 grand a day to use the equipment that we paid for and built ourselves. such as the way user facilities work. So we were able to repeat this same experiment, which took us 6 months, and got at 1,000 times the dose resolution in 7 hours. So we can see some pretty sick resolution of exactly when that surface acoustic wave speed starts to drop. That's when void swelling began, and we confirmed this with TEM as well. So this is how we want to break the bottleneck in radiation material science. If we do a quick in situ TGS experiment, we can identify places where curves change slope or change derivative. And then you can pull out specimens from there for TEM and minimize the really time-consuming destructive stuff that's the bane of every student's existence. You've done this before. I don't know if anyone's ever made a TEM specimen the old way, grinding down to a 300 micron disc, polishing on a lapping fixture, twin jet polishing until the laser pokes through. I did one. That was enough to motivate me to think about other ways to do it. So I've done it once. Where we're going next with this is beyond single crystals and things and onto real alloys like plastic and mechanical property changes. And here I'm going to talk about something called spinodal decomposition. Is anyone familiar with this process? It's the double derivative free energy region, and I see you like this, yeah? In the phase diagrams where you can get homogeneous phase separation from a good solid solution into alternating nanometer level laps of a high and a low chromium alloy for the case of an iron chromium alloy. And this slow and steady decomposition causes a huge increase in hardness and an associated decrease in ductility. This takes often hundreds of thousands of hours to manifest in reactors. You never really know the extent of it because you change by 10 degrees, you change the speed by a factor of 2. And if we have a way of measuring spinodal decomposition without cutting a piece of material out of a reactor, like literally cutting a hole the size of a golf ball out of the core barrel and making a test specimen, we'd have a way to be more sure about reactor life extension. So we threw TGS at this. My hypothesis was spinodal decomposition should change the thermal diffusivity of that phase decomposing. I was wrong, but we looked anyway, and we found something we didn't expect. This is what a TGS signal looks like from an unaged cast austenitic stainless steel. I would say on the grand scheme of things, pretty boring. And when you take a Fourier transform to look at the acoustic wave modes, pretty boring. The only other thing you see here, that thing, is the air acoustic wave from the lasers crossing in a hemisphere of air in front of the sample. When you age the sample, however, it may look the same in time space, but in frequency space, something else happens. You get surface acoustic wave peaks splitting, which we can't see any evidence of having happened before. And our going hypothesis is that peak is due to spinodal decomposition causing stiffening, which we're able to measure on our Vickers hardness indenter. And we wanted, this is another reason I wanted to talk to Professor Hostman, is understand this with nano indentation. But just from a correlation point of view, if we plot those first and second surface acoustic wave frequencies with energy, we end up seeing that there's not much of a change for that first acoustic wave mode, but the second one increases fairly linearly with our very few data points, with aging temperature. And to replot this with the value that people actually care about, Sharpie impact energy, the surface acoustic wave speed, let's say they increase at different rates. So we have some empirical correlation between surface acoustic wave frequency, which we can measure on the order of a second, and how brittle the material should be. So we really want to move into the alloy space where things get messier, where we're looking at microstructural transitions like precipitation, amorphization, phase segregation, all these other things, high entropy alloys self-destructing from thermal aging. And so the way you can work with us, if anyone is interested, is if you've got an effect that you'd like to know the kinetics of, and you want to see whether we can get a signal, send us a couple samples. They just have to be polished to a mirror finish, and within a day we can tell you whether or not we get a signal at all. Then pick your variable to vary, whether it's temperature, strain, corrosion in a transparent fluid, radiation, all of the above, and we can try a ex situ experiment, where we can either irradiate or you can send us pre-irradiated specimens and see whether or not we see a change with the variable of interest, at which point we can go in together and write one of these beam time proposals at Sandia National Lab to do an in situ experiment, where you can get a year's worth of data in an afternoon. And then sky's the limit. The idea here is then that radiation material science can proceed at the speed of thought, where you can make an alloy in the morning, test it in the afternoon, and repeat. Kind of like we do in all the other fields of science, so I think it's about time we caught up. Thanks a lot. I'll answer any questions you guys have.
questions? Other than what we already discussed?
Yeah. Anything on the laser project?
So one of the main hardening mechanisms of the laser array is obviously dislocation being produced, dislocation loops being produced. You will not be able to pick that up though, right?
I didn't mention it, but we see it.
How so?
Right there, that increase in stiffness. So this is due to dislocation force hardening coupled with pinning of bending segments by radiation defects. When you do this on unirradiated materials that have suffered cold work, the dislocation density increases at the same rate that the pin segment length decreases as well. The two effects cancel out. But when you add radiation to the mix, you pin those segments and you see an increased stiffness from an inability of those dislocations to bend. And so on materials that void swell at a higher dose, we actually see a saturation and a level off due to dislocation hardening, and then a drop when the void swell expands. So we can see the kinetics of that only during irradiation, not during less extreme environments.
Anybody else? Not, then thank you very much.